So today we're going to be talking about standing waves and vibrating air columns that are both open and closed at one end. So you have two formulas for open and closed. You have one that's for a harmonic series of a pipe open at both ends. So this is both ends. And it's going to be F, which is frequency, equals the harmonic number, which is N, times the velocity, or the speed of sound in the pipe. Over the length of vibrating air columns times 2, so it'd be 2. So it's going to be length of the vibrating air columns. So we'll just put air columns. So that's for open at both ends. And now we also have one that's for a pipe closed at one end. So that's going to be the same thing, which is going to be frequency is equal to the harmonic number over times the speed of sound. But instead of multiplying the length of air columns by 2, we're going to multiply it by 4. So it's going to be 4. So now we're going to use these two equations and we're going to apply them to some problems. So we have one that says a pipe open at both ends, so it's going to be this one, has a fundamental frequency of 125 Hertz. If the pipe is 1.32 meters long, what is the speed of the waves in the pipe? So we're trying to find the velocity for this one, so we're going to erase this. So both ends. And then one end. So now we're going to use both ends. So we know that the frequency of this pipe, which is open at both ends, is 125 Hertz. And we know that the number of harmonic number is 1. So that doesn't really count. And then we have the length of the pipe, which is 1.32. So now we're going to put that in. So we have 125 equals V over 2 times 1.32. And 2 times 1.32 is equal to 2.64. So 125, not Z. 125 equals V over 2.64. So 2.64. Oh my gosh. Okay. And V is equal to 330 meters per second. So that is the speed of the sound going through this open-ended pipe. So it's open at both ends. So it's going to be like this. And the speed of the sound is going to be 330 meters per second, and the length of this is 1.32. So that's what you do when it's open at both ends. But what do you do when it's open at one end and closed at the other? So we're going to do another sample problem that's going to talk about when a pipe is open at one end instead of 2. So it says, a note from a flute, a pipe with a closed end, has a first harmonic of 392.0 Hertz. So now we're using this one. It's going to be F equals 392.0 hertz. Now it tells us that the length, it's asking us the length, my bad, it's asking us the length. I mean, that's going to be in meters, and it's telling us that the velocity, the speed of sound in this pipe is 331 meters per second. So it's going to look something like this. 392 equals 1. And it's going to be, so we're just going to, actually, n equals 1. But we're not going to include that because it doesn't really make a difference. So it's going to be 331 over 4L. So now if you switch these two, it's going to be 4L equals 331 over 392. So that equals 0.844 equals 4L. And we're going to divide both sides by 4. And that's going to be 0.211. So the length of this pipe is 0.211 meters. And you can substitute this, and if you do it all over again, you can plug this into the L to make sure that you have it right. So let's just do that real quick. So it's going to be and that does come out to be right. So the length of the pipe, which is closed at one end, so it's going to look like this. The length of it is 1, 2, 1. And that is how you solve for standing waves in vibrating air columns that are both open and closed at one end.